So I just want to emphasize, I was a part of Trends Group, but I was in another group. I'm with Dr. Larson. So my name is Destiny Green, and I am a rising senior at Allen University, located in Columbia, South Carolina. And this is some research I did over the summer, understanding the control of surface chemistry towards unsaturated carbon-carbon bonds, oxygen, hydrogen over intermetallic catalysts. Okay, so first, y'all are probably like, what are even intermetallic catalysts? What are they? Like, what do they have to do with any of this? So these are compounds with a defined stoichiometry and crystal structure with specific sites. So this is kind of like an example of it right here, just a mixture. But as you can see with IMCs, that's what they're called, they have a bulk to them, and it's not really common for you to mess with that bulk because it's the standard. That's why we're really focusing on the surface, but you have to know which surface to use. So why are IMCs important? They're important because we can develop different novel materials. So before that I've heard, a lot of scientists and chemists have used like metal alloys, and that just consisted of like one element. It didn't really have a combination of anything. But now with IMCs, it's a combination. So it's like one, like it could be nickel and silica. It could be like nickel carbide. It could be different mixtures that you wanted it to be. So nickel-based catalysts are frequently used because of the carbon-carbon bond capability they both have. So these were some methods that I used while doing my experiments, but my hypothesis states if the reactive supports can be a source of p-block elements, then we will increase more periodic trends. So I just want to go first with these. This is the reduction procedure and anneal procedure. So with the reduction procedure, we used hydrogen, and it's very important that we use this one because it frees up the carbon atoms, allowing more space, so allowing more elemental compounds to even get in. Also with the anneal procedure, we use argon, and argon typically changes like an element's chemical or physical properties to like make them more workable. But with these two, with the experience that I ran, it's very vital. And as you will see, like on later presentations and my data and things like that, you will see that we have changed both of these drastically. Another thing is the calculations. So of course you have to have the calculations and the tests to make sure your experiments are even making sense, and a lot of people or others in research papers can understand it as well. So some two softwares that I used was Avogadro and Vesta. Avogadro is like a molecular editor and visualizer, and Vesta is like a 3D molecular like software that I used. So we both use these on examining the hydrogen, oxygen, and ethylene absorption that we did on the various intermetallic catalysts. And with this data that we received from the calculations, we created graphs with XRD, X-ray diffraction, and TM pictures, basically transitional metals. With the XRD, it shows us an illustrated graph of which compounds are used more, but you'll see later on, probably like in the next slide, you will see that you will see the comparison, basically. So this is the XRD machine that we've used previously before. I know y'all like a little diagram there, but I basically had to create the catalyst in a sense. Like before, I was just, I don't know what I'm doing. Like, what do I do? Like even Max had to help me sometimes. He was like, it's okay. But with the start of the preparation, you have to have the metal salt. And with the metal salt, you add hydrogen to basically form it into a liquid form. Once it is in a liquid form, you add the support. Of course, we measure things out because you just can't be adding a bunch of stuff in the lab that has very toxic chemicals. So once we did that, we mixed it thoroughly, but we had to let it air dry. Once we let it air dry, we had to crush it and store it for future tests, future runs. Interesting thing with XRD though, it's very expensive. So there was some times where we had to, oops, I don't know what I did. There was some times where we couldn't do it because it was a long time. I think the longest compound I did was about 8 hours. So I went to get lunch because I was not waiting that long. This is a graph, well, data that we used before. And as you can see, one uses 500 degrees Celsius with hydrogen for 2 hours, 1,000 degrees argon for 12 hours. So with the nickel 2 silica right here, don't really see anything, looks okay, you know, there's peaks going there, blah, blah, blah. But then when we get down here, this is because of hydrolysis. So the beginning of it, I believe like the hydrogens they were present, but they weren't like smooth as this. So some of this beginning data I really couldn't use in some of the graphs because it didn't really give us, I wouldn't say it, like vital information. So these are the XRD data I was stating before. So we tested 3 different trials. And the first trial was the effect of the reduction temperature, but we all fixated on the same anneal temperature at 1,000 degrees Celsius. So as you can see, when we did 500, 600, 700 degrees, nothing really changed. It was just a combination of nickel 2 silica and silica carbide, nothing too, drastic. But as we move on to the effects of the support, you can see that in silica nitride and silica dioxide, you have pure metal here. So it's just pure nickel, meaning that the silica, which is the support, it really didn't free as much, and it freed it too much. So it freed the metal too much and allowed more space instead of just becoming the nickel 2 silica and silica carbide. Once again, for the effect of the anneal temperature, we fixated on reduction temperature at 500 degrees Celsius. And as you can see, when we did 900, 1,000, and 1,100, with the 1,100, it was nickel 1.5 silica. So it means it devoured it too much. So it didn't stick with the nickel 2 silica and silica carbide because it just did 1.5. So we knew that different elements, of course, exhibit different behaviors, but while doing these test runs, we can figure out why they're even doing this in the first place. So again, this is more XRD data with cobalt and iron. And these are just the effects of the reduction temperature and the anneal temperature. Once again, cobalt 2 silica, silica carbide, nothing really major. Same with 700, nothing really too much on that. But you can see here, it's been a combination of the actual support, the cobalt silica, and cobalt 2 silicide. So with that, we knew either there was something wrong, or we did something wrong, like human error, or the way we prepared the sample was wrong. Also, with the effect of the anneal temperature, when we did 900, 1,000, and 1,100, it still was the blue graph that gave us an eye-opener. And we were just wondering why it would even be like this. Same with the iron. Similar to what we did with nickel, everything was pretty much the same when it was the reduction temperature. But as we moved on to the anneal temperature, you can see now it's nickel 5, silica 3. So these are some calculation results. Just like I said before, I used Avogadro and Vesta. The main trends I really looked at was the dioxide dissociative because it shows and tells how exothermic it is, meaning it's not strongly bounded to the surface that it's on. Okay, so these are some forthcoming plans. that I wish to continue with my group. So first we want to achieve the synthesis of silicides, so finishing doing all of those. Once we do those, then we want to move on to aluminides, attempting with aluminide supports, but of course more calculations and more tests have to be run. We want to then extend to the D block element, which is this stuff right here, basically right here. But with these findings, we can develop over 1,000 compounds that haven't even been studied yet, that haven't even been researched on. So I feel like in the near future, a lot of these tests will be very vital in what we do and what we bring. So, questions?